Okay, so continuing on with permutations and combinations, we're going to talk about combinations. And again, this is something we do in Algebra 2, something we do in pre-calculus if you took it. So permutations, remember, is when order does matter. Combinations are when order does not matter. And so if it says, you know, how many ways can you pick a group of 3 out of a group of 10, if there's not designated jobs, that's a combination. So there's a formula again. The number of combinations of indistinct objects taken r at a time is given by this, n factorial over r factorial times n minus r, where n is the total number and r is how many you're taking. So notice where r is less than or equal to n. Again, we're going to use this formula, and then we'll talk about using our calculator after that. So it says find and interpret the results of combination 4 choose 4 and combination 4 choose 2. So if we do combination 4 choose 2 or choose 4, you would get 4 factorial over 4 factorial over 4 minus 4 factorial. And so if you think about that, these are going to cancel out, and you're going to get 1 over 0 factorial, which you can do on your calculator, but it's really just 1. How many ways can you take 4 objects 4 at a time? And when order doesn't matter, as opposed to a permutation, this is when, right, ABCD becomes the same as BADC, because order doesn't matter. So that's why there's only one way. There's only one way to take 4 things and choose all 4 of them if order doesn't matter. But if you do combination 4 choose 2, you would now have 4 factorial over 2 factorial over 4 minus 2 factorial. And just to show it out here, 2 times 1 times 2 times 1. So 2 times 2 is 4, so that cancels this 4 out. So the answer is 6. And this would be 4 objects, and you are taking 2. I like to say 4 choose 2. Like you're choosing 2 out of 4 things. So if you had 4 people, but you wanted a group of 2, there are 6 ways that you can do that. Okay, so does order matter? Does order not matter? So look at this example. It says a Senate investigation subcommittee of 4 members is to be selected from a Senate committee of 10 members. Determine the number of ways in which this can be done. So again, you have to think about, does order matter? Is it a permutation, or does order not matter? Since it's just a group and no one is like president, vice president, this would be a combination. So we're going to do combination of how many total members are we choosing from, 10, and we want 4 as our subcommittee. So again, using the formula, we would do 10 factorial over 4 factorial, and then you subtract 10 minus 4, so then that would give me 6 factorial. And again, I just want to show you how you can do this if you didn't have a calculator with this button on it, or how did they do it before they had this button? Right? Like you could cross out the 6 factorial, crosses out with the 6 through the 1. And then I just always do some other crossing out, like 4 times 2 is 8, so that cancels the 8 out. And 3 divides into 9 3 times. And yes, you can use a calculator, but I can do this now without a calculator. That 3 times 7 is 21, times 10 is 210 ways that this can happen. So there's 210 ways that that committee can list out. And no, we're not going to make a tree diagram of that. What about this one? It says, how many poker hands of 5 cards can be dealt from a standard deck of 52 cards? So 52 card deck, we just want hands of 5, right? So again, it doesn't matter in which order you deal them out in this kind of poker. Excuse me. And so just 5 cards from 52. Order doesn't matter. So that's a combination. And I would do 52 choose 5. This would be one that's going to be a pretty big number. Oh wait, if you were going to write it all the way out. So let's think about how we could write it out and show our work without writing from 52 down to 1, right? So 52 factorial over 5 factorial, and then 52 minus 5 would be what? 47 factorial. So think about this. On the bottom, 47 factorial is going to cross out with all the 47 down to 1. So I'm really just going to have 52 times 51 times 50 times 49 times 48. And then I'm going to say times 47 factorial, because then that's going to cancel all those out. But then I'm also going to have down here still like times 5, times 4, times 3, times 2, times 1. And if you don't like doing the canceling out thing, you don't have to. I just do it sometimes to try to make my life easier, to simplify. But you don't have to do it if you don't want, okay? But like all of these would divide into these, and so that's why I tend to do it. But you can just do the top and do the bottom and type it on your calculator, and it's a whole lot. It's like 2,598,900, I think. 2,598, 960. Sorry, I read my calculator wrong. Which is why getting a really good hand in poker with just 5 cards is a pretty rare chance of that happening, okay? But that's how many different hands there are. So now we can take this idea of combinations and permutations and apply them more than once, okay? So it's like going to be using the multiplicative principle along with permutations and combinations. So it says the members of a string quartet consisting of 2 violinists, a violist, and a cellist are to be selected from a group of 6 violinists, 3 violinists, and 2 cellists. And how many ways can the string quartet be formed? So this is different than what we did in 6-3, because in 6-3 we would just be choosing 1 violinist, 1 violist, and 1 cellist. Those are weird words for me to say. So think about if we want 2 violinists out of 6 violinists. Again, order doesn't matter, so that would be out of 6, I want to choose 2. And then there are 3 violists, and I only want 1. So I could say combination 3, choose 1. And if there are 2 cellists to choose from, and I just want 1, that would be 2 and 1. And just like what we did in 6-3, I want all of these at the same time. So this is like multiplication. It's that multiplication principle. Fundamental counting principle is what I call it. And really, 3 choose 1 and 2 choose 1, I think that's just going to be 3 and 2. I'll use the formula to show you, but I'm pretty sure it works out really nice. That's like if you just choose 1, it's just 3. There's just 3 ways you could do it, but I'll show you the formula still works. You would do 1 factorial over 2 factorial, and then on this one, 2 factorial over 1 factorial. 2 minus 1 is 1 factorial. So over here, we would get 6 times 5 times 4 factorial is going to cancel out with the 4 factorial. And then times 2 times 1. So 30 divided by 2 is 15. Times, on this one, 3 times 2 times 1, right? 3 times 2 times 1 over 2 times 1. So you're only just going to get 3. And the same thing on this one, you're just going to get 2. So that's maybe something to think about, but if you like writing it out as a combination, you can. And then what is that? 90, right? 15 times 3 is 45 times 2. There are 90 ways that string quartet could be formed. But what if they made a different restriction? So look at part B. Part B says, what if now one of the violinists is designated as the first violinist and the other is designated as the second violinist, like first chair, second chair. Now we've switched this, and this is now a permutation because now order matters. So now, out of the 6 violinists, I'm still choosing 2, but now I'm doing the permutation, not the combination. Everything else is still 1, right? There's just 3 ways to choose the violist from 3, and since I'm only choosing 1 cellist from 2 cellists, I'm now choosing 2. But notice that this is now changing. So now my formula is just 6 factorial over 2 factorial times 6. So 6 times 5 times 4 times 3 times 2 times 1. And then I still have a times 6 out here. And so now I'm going to get 180 ways for that to happen. So notice that if you change it to order matters, there's a lot more ways that it can happen. And so that's going to be the tricky part now, is trying to figure out, does order matter or does order not matter? Okay? So let me see where my time is. 9 minutes, 10 minutes. So I'm going to stop here, but please read this and try to think about if you can figure out how to set it up, and then we'll start here in class.